Now let us generalize the equation of the first law of thermodynamics. So far we have been writing the equation based on the Joule's experiment, like for any process undergone by closed system, heat transfer minus work transfer is equal to change of energy. In Joule's experiment, this work transfer was shaft type of work transfer. But we know that there are different other types of work transfers as well. For example, displacement type of work transfer, electric type of work transfer, or expansion type of work transfer. To generalize the equation, we can write all these work transfers together as shown in this equation. So this equation I have written like this: Q minus the sum of all the possible work transfers like W shaft, W electrical, or W expansion, or displacement, or any other known type of work transfer is equal to change of energy. Remember, there is no harm in writing all the work transfers together, because if any type of work transfer or a couple of work transfers are not present in the given process, then you can straight away cancel them, because there is just addition of work transfer. For example, if in the Joule's experiment electric type of work transfer was not present, so I can cancel out this by putting 0 here. Expansion type of work transfer was not present in the Joule's experiment, so I can cancel out this and can write the remaining terms and draw the required conclusion. So this is about the generalization of the work transfer. Now we'll pay the attention on the right hand side. Let us generalize this term also. Now as far as Joule's experiment was considered, which type of energy was changing in the Joule's experiment? We did not discuss that yet. Was it kinetic energy that was changing? Was it potential energy that was changing due to addition of the work? No. Neither kinetic energy of the system changed nor the potential energy of the system changed. Why? Because the system under consideration was the entire vessel or the fluid inside the vessel, and when the weight was dropped, when the paddle wheel rotated, the entire body of the fluid did not move from one place to the other place, or it did not fall down from a height. And that's why if you consider the system as a whole, as in macroscopic thermodynamic viewpoint, the kinetic energy and potential energy of the vessel inside the Joule's experiment did not change. So which kind of energy actually changed? Because we said that due to the shaft type of work transfer, the energy changed, but which kind of energy changed? To answer this question, we have to define a new kind of energy, and that energy is called as internal thermal energy. So here we are defining a new kind of energy, and that is internal energy or internal thermal energy, which is denoted by capital letter U, and this delta is for the change of internal energy. And to generalize the right hand side of this equation, we will again write the sum of all the types of energies which are already known by other branches of the science, plus this newly identified energy change, and the equation becomes more general and it looks like this. So Q minus sum of all the types of work transfer is equal to sum of all the types of energy changes: kinetic energy change, potential energy change, as well as internal energy change. Remember, in Joule's experiment, kinetic energy and potential energy did not change, but we are writing all the terms on the right hand side to make the equation more general. Now suppose in a process a couple of energy changes are not present, then you can straight away cancel them as we cancelled out the work transfer. For example, in certain process, suppose the internal energy change is not present, so you can cancel out, put it 0. The potential energy change was not present, you can cancel out and put it 0. And then from the remaining terms you can draw the required conclusion. So equation number 3 is the holistic form or general form of the first law of thermodynamics, because it involves all the types of energy changes as well as all the types of energy transfers. If you look at the left hand side of the equation, you will find that these are all the known types of energy transfers. Only two types of energy transfers are identified by macroscopic thermodynamics, that is heat transfer and work transfer. And we know that these are not the properties of the systems. They are path functions, they are not state functions. So these are non-properties. Whereas on the right hand side, there are all the types of energy changes of the system, and these energy changes or these energies are the properties of the system. Kinetic energy is a property of system, potential energy is a property system, and this newly identified internal energy is also property of system. Now, since all the types of energies and energy transfers are grouped inside a single equation, we can say that any one form of the energy can be converted into other form of the energy or energy transfer. For example, this heat transfer can be converted into work transfer, shaft type of work transfer, or say electric type of work transfer can be converted into internal energy, or say kinetic energy change can be converted into potential energy change with the help of suitable experiments that you can design also. That means any one type of energy can be converted into the other type of energy or energy transfer, and that's why this equation is a mathematical representation of law of conservation of energy, which states that energy cannot be created, cannot be destroyed, only one form of the energy is converted in the other form of energy.